In this section, we're going to look at the derivatives of both logarithmic and exponential functions, and we're going to start with the natural log. And the natural log function has a base of e, and I can rewrite this expression by writing it as y equals log base e of x. And every logarithmic equation can be written in exponential form, and we know that if I write this in exponential form, the equivalent expression is going to be e to the y is equal to x. Y is the exponent on e that results in x. And so what I want to do now, now we've looked at the derivative of e to the x, and we know that the derivative of e to the x is e to the x. It's its own, it's the one function that is its own derivative other than 0. And what we're going to do, we're going to combine that formula for the derivative of e to the x with the chain rule by using implicit differentiation. And we're going to take the derivative of both sides. We're going to go d dx of e to the y is going to equal d dx of x. We're going to just take the derivative of both sides of that equation. Now we know that y is some function. So when I take the derivative of e to the x, I would get e to the x. When I take the derivative of e to the y, I get e to the y times y prime. When I take the derivative of x with respect to x, I just get 1. When I solve for y prime, I get 1 over e to the y. But I want my derivative in terms of x, not in terms of y. And I know that x is equal to e to the y right here, so I can rewrite this as 1 over x. We have a new derivative formula, d dx of the natural log of x is equal to 1 over x, and I'll state the domain for this. This function, remember, has a limited domain. The domain for the natural log function is x is greater than 0. And from now on, now that we have the chain rule, we know that all of our derivative formulas, those that are written with respect to x, we can also extend those formulas by taking the derivative of that function with respect to another function. So we can write this as 1 over u times u prime, or just u prime over u. And again, u has got to be greater than 0. When we think of the natural log function, let's graph that function and take a peek at it. Now I've got the graph of y equals the natural log of x here, and if you notice, you can see the domain. The domain is x is greater than 0. You can see here, this function is always increasing, so the slopes are always going to be positive, and we can see that that's going to make sense because when we look at the derivative here, 1 over x, that fraction is always going to be positive since your domain here, you're only using values of x that are greater than 0. So this denominator, or this fraction, is always going to be positive. So the derivative, the slopes of the tangent lines, will also always be positive. All right. Now, I want to look at a slightly different version, and that is what happens when we take the derivative of the natural log of the absolute value of x. Now we can use a piecewise function to define this, and if I do that, I'm going to write y equals the natural log of x if x is greater than 0, just using the definition of absolute value, and y is going to equal the natural log of the opposite of x if x is less than 0. And we don't include being equal to 0 because you cannot take the log of 0. All right. So basically here, if x is less than 0, if x is a negative number, I am allowed to take the natural log of the opposite of it. And so now when I take the derivative of this, dy dx, I'm going to take two separate derivatives. The derivative of the natural log of x is 1 over x, and that's if x is greater than 0. The derivative of the natural log of negative x, that is a chain rule problem because you have to take, we're letting u equal negative x, so we would have 1 over the opposite of x, or negative x, times the derivative of what's inside, which is going to be negative 1. So this derivative is going to be 1 over x if x is less than 0. So basically what's going on here is that the derivative of the natural log of the absolute value of x is 1 over x. And this, basically the only difference here is that we've extended the domain. By putting in the absolute value, we are now allowing ourselves to input negative values for x. We can never, we can't use 0. You cannot take the log of 0. And so this new formula, the derivative of the natural log of the absolute value of x is going to be 1 over x. The only difference is that the domain is just x cannot equal 0, right? X can be positive or negative. And if we extend that using the chain rule, the natural log of the absolute value of u is going to be 1 over u times u prime, and u basically cannot equal 0. So let's take a look at the graph of the absolute value of the natural log of the absolute value of x. So take the natural log. To find absolute value, you go into math, and then you go over to number, and you can see number 1 here, the first one. If I hit 1, it's going to give me the absolute value, and I type in x, and then I'm just going to arrow out and close my parentheses. And so I'm going to go back and just do a, I'll do a zoom 6. We'll just do a standard window here. So now what I've done, we've talked about extending the domain of the natural log function. This piece over here is the natural log of x, and then this little piece right here, we're now allowed to take the opposite of those negative values. And I'm going to zoom in on this so you can get a better idea. Okay. And so notice we've got there's a vertical asymptote here. We're not allowed to use 0. 0 is not in the domain. And you can see that for positive values of x, the slopes are going to be positive. And for negative values of x, the slopes would be negative. And that does make sense, because if you've got 1 over x, and you enter, or you let x be a negative number, then you're going to get a negative value.